Imagine for a second that you're chilling on your couch, minding your own business, when suddenly a dragonfly the size of a hawk swoops through your window. And I'm not talking about some mutant freak of nature created in a lab. No. I'm talking about a completely normal dragonfly that just happens to have a wingspan wider than your arm span. Terrifying, right? Well, believe it or not, this wasn't some nightmare scenario. This was reality, and it all happened because of something we literally cannot live without: oxygen. Yeah, you heard that right. The very thing keeping you alive right now nearly killed everything on Earth once upon a time. And then, millions of years later, when Earth decided to crank the oxygen levels way up again, it turned insects into absolute giants. We're talking millipedes longer than your bed, scorpions as long as a small dog, but way lighter, like a nightmare balloon animal, and dragonflies that could probably knock a small bird out of the sky if they felt spicy. So how did we go from oxygen being Earth's biggest threat to it creating a planet full of supersized bugs? Well, buckle up, because this story is wild. Before we go any deeper into the part where oxygen almost rage quit the entire planet, do me a favor. Hit the like button, because every time you do, a hypothetical giant dragonfly does not spawn in your living room. And honestly, that's the kind of safety we all deserve. Subscribe too. It keeps this channel alive, unlike most life during the Great Oxidation Event. To really understand this whole mess, we need to go way back, like 2.4 billion years ago back. And at this point in Earth's history, if you were to somehow travel back in time, you would die immediately. And not just because of the lack of Wi-Fi. No, you would suffocate because the atmosphere was almost completely devoid of oxygen. I mean, sure, there were trace amounts here and there, but nothing close to what you'd need to, breathe. Instead, the air was packed with things like methane, carbon dioxide, and other gases that would make modern Earth smell like a teenage boy's locker room mixed with a chemical plant. Not pleasant. And the oceans? Oh boy, they were even worse. They were essentially toxic soup, filled with dissolved iron and other metals, making them look more like rust-colored sludge than the beautiful blue waters we know today. So yeah, early Earth was not exactly a vacation destination. But despite all of this, life did exist, and it had been around for quite some time actually. We're talking about simple microorganisms, mainly bacteria and archaea, who were perfectly content living in this nightmare world. They didn't need oxygen. In fact, many of them would have found it downright poisonous, and they were thriving, doing their little microbial thing, breaking down chemicals, and generally just vibing in the primordial ooze. Now, amongst these early microbes, there was one particular group that would end up changing everything. And I mean everything. These were the cyanobacteria, also known as blue-green algae, and these little guys had developed something absolutely revolutionary: photosynthesis. Yeah, the same process that every plant on Earth uses today to convert sunlight into energy. And as a byproduct of this process, they released oxygen. Just tiny little puffs of it at first. No big deal, right? Wrong. Because here's the thing. Oxygen is incredibly reactive, like absurdly reactive. It wants to bond with pretty much everything it touches. And for organisms that had evolved in an oxygen-free world, this stuff was essentially poison. It's not like the cyanobacteria were intentionally trying to wreck everything. They were just doing their thing, photosynthesizing away, completely unaware that their waste product was about to reshape the entire planet. At first, this wasn't a huge problem because the Earth had plenty of things for the oxygen to react with. The oceans were full of dissolved iron, and the oxygen would immediately bind to it, creating iron oxide. Rust. And this process went on for millions upon millions of years, with the oxygen basically being absorbed by all the available iron in the oceans. And we actually have evidence of this today in the form of massive banded iron formations, these huge deposits of iron oxide that formed on the ocean floor. They're like geological receipts showing that, yeah, this definitely happened. But eventually, after hundreds of millions of years, the Earth ran out of things to soak up the oxygen. The oceans had been oxidized, the rocks had been oxidized, everything that could rust had rusted, and with nowhere else to go, the oxygen started accumulating in the atmosphere. And this is where things get really interesting, or really horrifying, depending on your perspective. What happened next is known as the Great Oxidation Event, or sometimes the oxygen catastrophe. And catastrophe is honestly the perfect word for it, because this event triggered one of the most devastating microbial die-offs in Earth's history. We're talking about a planet-wide massacre of microorganisms. The anaerobic bacteria, the ones that couldn't handle oxygen, were suddenly exposed to an atmosphere that was becoming increasingly toxic to them. And they died. Like, a lot of them died. The scale of this die-off is hard to even comprehend. These organisms had been the dominant life forms on Earth for billions of years. They'd had the planet to themselves. and suddenly their own atmosphere turned against them. Some estimates suggest that this event wiped out the vast majority of anaerobic life on Earth at the time. It was extinction on a scale that makes the dinosaur extinction look like a minor inconvenience. And to make matters even worse, the Great Oxidation Event also triggered what's known as the Huronian glaciation, a long ice age with repeated glaciation spanning almost 300 million years. Yeah, you heard that right. Not one continuous freeze, but wave after wave of ice ages over an absolutely absurd time span. And this happened because the methane that had been in the atmosphere, which is a powerful greenhouse gas, was being broken down by all this new oxygen. And without that methane trapping heat, Earth's temperature plummeted, and the planet went through these repeated cycles of basically turning into a giant snowball. So not only were organisms dealing with toxic oxygen, but they were also freezing to death. Fun times. Now, you might be wondering, if oxygen killed off most of life, how are we here? Well, because some organisms adapted. Evolution, baby. Some microbes developed ways to tolerate oxygen and eventually even use it to their advantage. And it turns out that oxygen-based metabolism is actually way more efficient than the anaerobic processes that came before it. With oxygen, organisms could extract far more energy from their food, and this opened up a whole new world of possibilities. Over time, a more complex life began to evolve. Single-celled organisms eventually gave way to multicellular ones. And these new organisms could do things that the old anaerobes never could. They could grow larger, move faster, and occupy new environments. And all of this was possible because of oxygen. So yeah, oxygen nearly killed everything, but it also paved the way for pretty much all complex life on Earth, including us. But here's where our story takes another wild turn, because fast forward about 2 billion years to the Carboniferous period, roughly 350 to 300 million years ago, and Earth decided to do something absolutely bonkers with its oxygen levels. It cranked them up, way up, like to levels we've never seen before or since. During this time, oxygen made up about 30 to 35% of the atmosphere. For comparison, today it's only about 21%. And you might think, hey, more oxygen sounds great, right? More energy, bigger lungs, everyone's happy. Well, not exactly, because while higher oxygen levels did allow for some pretty amazing adaptations, it also created some of the most terrifying creatures to ever walk, crawl, or fly on this planet. Let me paint you a picture. You're walking through a Carboniferous forest, which, by the way, looks nothing like a modern forest. These are massive swamps filled with towering tree-like plants, giant ferns and club mosses that reach heights of over 100 feet or 30 meters. The air is thick and humid, and it smells like decaying vegetation mixed with mud. And as you're carefully stepping over roots and trying not to slip, you hear a buzzing sound, a really loud buzzing sound. You look up, and there it is. A dragonfly. But not just any dragonfly. This thing has a wingspan of over 2.5 feet or 75 centimeters. That's bigger than most hawks. This is Meganeura, the largest flying insect to ever exist, and it's hunting. These massive dragonflies were apex predators of the Carboniferous skies, swooping down to snatch up smaller insects and probably even small amphibians. And they could do this because of the high oxygen levels, which allowed their primitive respiratory systems to support much larger body sizes. But the terror doesn't stop in the sky. Oh no. Because as you're standing there, frozen in fear at the sight of this prehistoric monster, you feel something crawling over your foot. You look down and there's a millipede, but it's not the little harmless ones you find in your garden. This is Arthropleura, and it's over 8 feet long or 2.5 meters, longer than most humans are tall. And it's as wide as a dinner plate. This thing is essentially a living armored train, scuttling through the forest floor, munching on decaying plant matter. Thankfully, it's a herbivore, but still, imagine stepping on that in the dark. And we're not done yet, because lurking in the shadows, you might also encounter Pulmonoscorpius, a scorpion that could reach lengths of over 2 feet or 70 centimeters. That's a scorpion nearly as long as your arm, with a stinger and venom. And while we don't know exactly how potent its venom was, I think it's safe to say you wouldn't want to find out. So yeah, the Carboniferous period was basically a horror movie brought to life. And all of this was made possible by that extra oxygen in the atmosphere. But why did high oxygen levels lead to giant insects? Well, it has to do with how insects breathe, or rather, how they don't breathe like we do. You see, insects don't have lungs. Instead, they have a system of tubes called tracheae that deliver oxygen directly to their tissues. Air enters through small openings called spiracles, and then it diffuses through these tubes to reach the cells. And this system works great for small insects, but as insects get larger, this diffusion process becomes less efficient because the oxygen has to travel farther to reach all the tissues. And in a normal atmosphere with 21% oxygen, this puts a pretty strict limit on how big insects can get. But when you pump up the oxygen levels to 35%, Suddenly that constraint is lifted. There's so much oxygen in the air that even large insects can get enough of it through their tracheal systems. And so, insects evolved to take advantage of this, growing to sizes that would be impossible today. It's kind of like if you suddenly had access to a much more powerful engine for your car, you'd probably build a bigger, faster car, right? Same principle. Now you might be wondering, why was there so much oxygen during the Carboniferous period? Well, it comes down to plants, specifically the evolution of trees and forests. During the Carboniferous, plants had recently evolved a compound called lignin, which is basically what makes wood, well, woody. It gives plants structural support, allowing them to grow much taller and create the first real forests. But here's the thing. When these plants died, almost nothing could break down lignin yet. The fungi and bacteria that decompose wood today hadn't really evolved those capabilities. Some primitive fungi existed, sure, but no lignin-destroying fungi had appeared yet. So dead trees piled up faster than they could rot. When these massive trees fell over, they just sat there. They didn't decay at anything close to a normal rate. They just piled up and got buried under sediment and water, and over time they turned into coal. In fact, most of the coal deposits we mine today come from the Carboniferous period, hence the name, Carboniferous, coal-bearing. And because these dead plants weren't being decomposed normally, the carbon they had absorbed during photosynthesis wasn't being released back into the atmosphere as carbon dioxide. Instead, it was being locked away underground, and meanwhile, living plants were still doing photosynthesis, still pumping out oxygen. So you had this massive influx of oxygen with no corresponding increase in decomposition to balance it out. And the result was an atmosphere that was absolutely supercharged with oxygen. This went on for millions of years, creating this bizarre world of giant insects and massive forests. But like all good things, it couldn't last forever. Eventually, organisms evolved that could break down lignin. Fungi figured out how to decompose wood. And once that happened, the carbon cycle started to balance out again. Dead plants began to decay, releasing carbon dioxide back into the atmosphere and consuming oxygen in the process. And as oxygen levels dropped back down, insects started to shrink back to more normal sizes. But there's another factor that probably contributed to the end of the giant insect era: birds, or more specifically, the evolution of flying vertebrates. During the Carboniferous, the skies were dominated by insects like Meganeura, but as we moved into the Permian period and beyond, flying reptiles and eventually birds evolved. And these vertebrates were much better flyers than insects. They were faster, more maneuverable, and they had better vision. And they probably found giant insects to be pretty tasty snacks. So suddenly being a giant insect wasn't such an advantage anymore. In fact, it probably made you a bigger target. And as oxygen levels dropped and predation pressure increased, insects that were smaller and more agile had a better chance of survival. And so over time, insect sizes decreased. And by the time we get to the Mesozoic, the age of dinosaurs, insects were already back to more modest sizes, no more dragonflies with wingspans like eagles. But here's something interesting to think about. If oxygen levels were to rise again, could we see giant insects return? Well, theoretically, yes. The physical constraints that limit insect size are still tied to oxygen availability. So if atmospheric oxygen somehow jumped back up to 35%, insects could potentially evolve larger body sizes again. But here's the thing. It probably wouldn't happen because of all those predators I mentioned. Birds, bats, and other insect-eating vertebrates are really good at keeping insect populations in check, and they've had hundreds of millions of years to perfect their hunting techniques. Plus, giant insects would face competition from vertebrates in pretty much every ecological niche. Want to be a big predator? Good luck competing with mammals and birds. Want to be a big herbivore? Same problem. So even if oxygen levels rose, it's unlikely we'd see a return of the megabugs. Though, honestly, I think most of us are okay with that. Now let's circle back to that first catastrophe, the Great Oxidation Event. Because while we've talked about how oxygen nearly killed everything, we haven't really talked about what it means for us. And the truth is, we owe our entire existence to that ancient disaster. Without the Great Oxidation Event, complex life as we know it probably never would have evolved. Multicellular organisms, animals, plants, fungi, all of us depend on oxygen for our metabolism. And it's kind of poetic in a way. The same substance that caused one of the worst microbial die-offs in Earth's history also made it possible for life to flourish in ways that would have been impossible before. It's a reminder that catastrophe and opportunity are often two sides of the same coin. What's deadly for one form of life can be a blessing for another. And this pattern has repeated itself throughout Earth's history. Mass extinctions clear the way for new forms of life. Environmental changes create new niches to fill. And organisms that can adapt to these changes thrive while others perish. It's brutal, sure, but it's also how evolution works. It's how we ended up with the incredible diversity of life we see today. So the next time you take a deep breath, remember that you're breathing in a gas that once nearly sterilized the planet, and that the oxygen in your lungs is the result of billions of years of photosynthesis, starting with those ancient cyanobacteria who had no idea they were changing the world. And remember that there was a time, not too long ago in geological terms, when that same oxygen allowed dragonflies to grow as big as birds and millipedes to grow longer than crocodiles. Earth's history is full of these wild swings, these moments where the planet does something absolutely bonkers and everything has to adapt or die. And we're living in the aftermath of all of that chaos. We're the descendants of the organisms that survived the oxygen catastrophe, that made it through the ice ages, that outlasted the giant insects and the dinosaurs and everything else the planet threw at them. And who knows? Maybe one day, Earth will throw us another curveball. Maybe oxygen levels will change again. Maybe something else will happen that we can't even predict. But if there's one thing we can learn from the past, it's that life is resilient. It finds a way, it adapts, and sometimes it even thrives in the face of catastrophe. So yeah, oxygen almost killed everything. Twice, technically, if you count the giant bugs as a near disaster. But instead, it gave us a world worth living in. A world with forests and animals and, thankfully, dragonflies that are small enough to ignore. Though, honestly, I wouldn't mind seeing one of those giant millipedes in a museum, from a safe distance, behind very thick glass. Thanks for hanging out with me, and until next time on Dead Curious.